Welcome to Money and Markets, Series 1, Lesson 9. This episode is called Retirement by the Numbers. Over the last 8 lessons, you learned the time value of money, compound interest, inflation, the yield curve, forward rates, variable rates, bank spreads, maturity, and what happens when borrowers break. Today, all of that comes together in one question. How much do you need to save each year, starting now, to retire comfortably? This is not hypothetical. We are going to meet a real character, walk through every step of his calculation, and leave you with a number you can argue with at the kitchen table. No spreadsheet worship, just transparent algebra. Meet Robert. Robert is 25 years old, fresh out of university, and just landed a job at an investment bank in 2024. Robert has a goal. He wants to retire at the end of 2064, 40 years from now, with $1 million in today's purchasing power sitting in his retirement account. Not $1 million in some inflated future currency. $1 million in what a dollar buys right now. He has 2 assumptions. First, he believes a 3% rate captures inflation over time. Second, he thinks his investments can earn 5% per year. He plans to deposit the same amount, $, at the end of every year from 2024 through 2063. That is 40 level contributions. In 2064, the year he actually retires, he deposits nothing. The question is simple. What is H? How much does Robert need to save each year? Step 1. Translate the goal from today's money into future money. Robert wants $1 million in 2024 purchasing power, but he is not retiring until the end of 2064. Prices will have risen by then. If inflation runs at 3% per year for 40 years, then $1 million today is worth much more in nominal terms in the future. The formula is the same forward value we learned in Lesson 1. Future value equals present value times 1 plus the rate, raised to the number of years. So we take 1 million multiplied by 1.03 raised to the 40th power. That gives us approximately $3,262,000. 3.26 million. That is the nominal target Robert actually needs in his account on the day he retires. 1 million today becomes 3.26 million in 40 years, just because of inflation. The goal did not change. The ruler got longer. Step 2. The annuity formula. Robert is going to deposit $, at the end of every year for 40 years. Each deposit earns 5% per year for however many years remain until retirement. The first deposit, made at the end of 2024, compounds for 39 years. The second, made at the end of 2025, compounds for 38 years. And so on all the way down to the last deposit in 2063, which compounds for just 1 year. If you line them all up, you get a sum. H times 1.05 to the 39, plus H times 1.05 to the 38, all the way down to H times 1.05 to the first. Factor out H, and the remaining piece is a geometric series. It has a clean closed-form solution. The sum equals 1.05 to the 40th minus 1 divided by 0.05. That fraction works out to roughly 120.8. So the total value of all deposits at retirement is H times 120.8. And we need that to equal $3,262,000. Step 3. Solve for H. We have H times 120.8 equals 3,262,000. Divide both sides by 120.8. H equals 3,262,000 divided by 120.8. The answer is $25,717.79. $25,718 per year, rounded up. That is what Robert must deposit every single year for 40 years to retire with $1 million in today's money. Not a guess, not a vibe. a number that falls directly out of compound interest and a geometric series. Two formulas you already know. The 3% handles inflation. The 5% handles investment growth. The 40 years give compounding enough room to do the heavy lifting. Let us put that number in terms you can feel. $25,718 a year. Divide by 12. That is roughly $2,143 per month. Divide by 52. About $495 per week. Under $500 a week. That is a car payment or a nice dinner for 2 or 2 months of streaming subscriptions, depending on how you look at it. For a 25-year-old at an investment bank, that is a real but manageable commitment. The key is consistency. Every year without fail for 40 years. Miss a year and the math gets harder. Start 5 years late, and you have only 35 years of compounding instead of 40. That changes the number significantly. The formula does not negotiate. It just compounds. Now, sensitivity. Robert assumed a 5% annual return. What if he is wrong? If his investments only earn 4% instead of 5%, the annuity factor shrinks. The geometric sum at 4% over 40 years comes out to about 95 instead of 120. That means H rises to over $34,000 a year, an $8,000 annual jump, just from 1 percentage point less return. Go the other direction. At 6%, the annuity factor grows to about 155. H drops to roughly $21,000 per year. The swing is dramatic. Between 4 and 6% return, the required annual savings ranges from $21,000 to $34,000. This is why sensitivity analysis matters more than false precision. You cannot predict returns to the decimal, but you can see how far wrong you would be if conditions shift. The right response is not to pick the optimistic number. It is to save as if returns might disappoint, and be pleasantly surprised if they do not. Problem B. A different way to think about retirement. Suppose Robert changes his mind. Instead of targeting a lump sum at retirement, he wants to fund a specific lifestyle. He decides he needs $150,000 per year of spending for 20 years after he retires. From 2065 through 2084. This is a present value of annuity problem. He needs to figure out how large the retirement pot must be at the end of 2064 to support 20 annual withdrawals of $150,000 each, if the remaining balance still earns 5%. The cash flows layer on top of each other, but the concept is the same. You are discounting each of those 20 withdrawals back to the retirement date and summing them up. The present value of an annuity of $150,000 per year for 20 years at 5% is roughly $1,870,000. That is the lump sum Robert needs at retirement. From there, you run the same annuity of deposits formula backward to find his annual contribution. Here is the real lesson behind the numbers. Start early. Robert begins at 25. If he waited until 35, he would have only 30 years of compounding. That cuts the annuity factor dramatically and pushes his required savings much higher. Compound interest does the heavy lifting, but only if you give it time. Over 40 years, Robert deposits about $1 million total, yet he ends up with $3.26 million. The rest is pure compounding. The money his money earned. Assumptions matter. 3% inflation and 5% return are plausible, but they are not promises. Change either number by a point or two and the answer shifts by thousands. And finally, the spreadsheet is not the life. Medical shocks, career changes, divorce. Non-market risk dwarfs a basis point debate. Still, knowing the algebra keeps grifters out of your kitchen and lets you negotiate from clarity instead of fear. The point of this exercise is not to predict the future. It is to make your assumptions visible so you can argue with them honestly. Let us recap what we covered. First, we translated a purchasing power goal into a nominal target using the inflation rate. 1 million today becomes 3.26 million in 40 years at 3%. Second, we used the future value of an annuity to turn that target into a required annual deposit. At 5% return, Robert needs $25,718 per year. Third, we stress-tested the return assumption and saw how sensitive the answer is. A single percentage point changes the required savings by thousands. Fourth, Problem B showed that funding a spending stream is the same toolkit in reverse. Present value of annuity tells you how large the pot needs to be. This is the last applied problem in our saving and borrowing arc. Next lesson, we wrap up everything from Series 1, from the time value of money through default and retirement math, and build the bridge into credit ecosystems. See you in Lesson 10.